Hello everyone, this is Lab 3. The purpose of this lab. The purpose of this lab is to apply Newton's law of motion and universal gravitation to understand orbital motion and gravitational interactions, multi-body systems like stars, planets, and moons. The models and key physics used in this lab. The main topics of this lab were Newton's law of universal gravitation and Newton's second law. They helped us simulate orbits and see how gravitational attraction led to circular/elliptical trajectories. We were also able to see how small changes in mass or velocity could lead to a stable orbit or a crash. In part 1, we analyzed the motion of a star orbiting a black hole of unknown mass. By using the star's trajectory data, we estimated the black hole's mass, similar to how astrophysicists determine the masses of unseen celestial bodies. In part 2, we simulated a spaceship moving under the gravitational influence of both a planet and its moon. The goal was to find an initial velocity that would allow the spaceship to orbit without crashing, testing how Newtonian gravity works in a multi-body system. These simulations demonstrated how small adjustments in initial conditions can drastically change outcomes, from stable orbits to collisions, which reinforced Newton's law in complex gravitational systems. The equations used in this lab were Newton's law of universal gravitation and Newton's second law. The gravitational force equation, F equals g m1 m2 over radius squared, tells us how strongly two masses attract each other. And then we use F equals ma to determine how this force affects acceleration, velocity, and position over time. In the code, these equations are applied repeatedly using small time steps to simulate orbital motion numerically. In part 1, the star was treated as the system, while the black hole and surrounding space were the surroundings. The black hole exerted the only significant force on the star, allowing us to focus on their two-body gravitational interactions. In part 2, the system was the spaceship, influenced by gravitational forces from the planet and moon, which were their surroundings. Defining the systems and surroundings clearly helped us apply Newton's law and correctly to each object's motion. The simulation started with defined masses, positions, and velocities for each object. In part 1, the star's mass was 2 times 10 to the 30 kilograms, and it orbited a stationary black hole at the origin. The time step was 1 day. And in part 2, the moon began with a circular orbit around the planet, and the spaceship started on the moon's surface. Finding a stable orbit required testing different initial velocities, particularly for the spaceship, to avoid collisions or escape. So this was part 1 of my GlowScript code. And this is the actual code. So the GlowScript code used the star's changing position to calculate its momentum change, and using FNet, we could solve the gravitational formula. We could solve for the black hole's mass. This approach mirrors how astrophysicists determine the masses of unseen celestial bodies using gravitational effects. So this was part 2 of my GlowScript code. And in part 2, the codes modeled gravitational interactions between the planet, moon, and spaceship. The net force on each object combined contributed from the two bodies. Motion was updated step by step using the momentum principle, and through trial and error, we found an initial spaceship velocity of about 19,000 in the x direction and 30,000 meters per second in the y direction, which produced a stable orbit. From part 1, we estimated the black hole's mass as approximately 1.26 times 10 to the 34 kilograms, and the moon's orbital speed was about 2.44 times 10 to the 4 meters per second, with an orbital period of about 64.37 hours. Possible sources of error uses trial and error to find the figure 8 orbit. There could be calculation errors. It's only a simulation and it doesn't reflect reality, and it assumes that no external forces were acting on the system, which is not very realistic. So for the what if we expanded this model to include more objects, the code would need to calculate the net force on every object that's added. So for example, the planet's net force would be the sum of the gravitational pulls from the black hole, star, and moon, and larger masses like the black hole and star would dominate the system, while smaller bodies like the moon would still experience noticeable effects. And this would greatly increase the complexity, but create a more realistic model of the multi-body system. The key concept is that F net equals dp over dt, and the net force represents the cause, and the dp dt represents the effect. We use the observed motion to find unknown quantities like mass by matching it to the theoretical force equation. The perpendicular force component curves the path while the parallel component speeds up or slows down the motion, explaining why orbits can be stable or elliptical. Thank you for listening.